So today I'm going to talk about the Kelly criterion. And the idea here is we're sizing bets to maximize long-run growth. And this is based off of Kelly's 1956 paper. So imagine you're betting on a coin flip. Ordinarily it's 50-50, but you have a trick, a signal that gives you an edge. That signal nudges your probability of being correct to a number we'll call Q, and the chance of losing becomes P, 1 minus Q. So the question we'll answer is simple. How much of your portfolio should you bet each round to maximize long-run growth while avoiding ruin? So we'll study a repeated binary gamble. Each round, you stake a fraction, L, of your bankroll. On a win, your bankroll multiplies by 1 plus L. On a loss, by 1 minus L. We'll denote the win probability by Q and the loss probability by P, 1 minus Q. To find the best constant stake fraction, we maximize the expected log growth per round, G of L, Q times ln 1 plus L, plus P times ln 1 minus L. Let's look at G of L for a few examples of Q. So here are the curves for Q equals zero point 0.6, zero point 0.7, and zero point 0.8. Each curve shows the growth rate as a function of the stake L. The peak of each curve is the fraction that maximizes long-run log growth. That's our Kelly fraction. So watch the optimum dot slide along each curve to the peak. For a fair binary signal, the closed form Kelly solution is simple. L equals 2Q minus 1, clipped at 0. You would only ever bet when Q is greater than 0.5. Now that we've seen the theoretical curves, let us test three concrete staking strategies in a repeated experiment. We run a Monte Carlo with Q equals 0.7, a 70% signal, over 100 independent bets, and simulate many possible wealth paths. So we'll compare three strategies: half Kelly, Kelly, and 1.5 Kelly. Thin translucent lines show individual trajectories. The thicker lines show the median path for each strategy. So you'll notice the Kelly strategy tends to maximize the median long-run growth. The 1.5 strategy sometimes reaches higher peaks, but it increases variance and the risk of ruin. Half Kelly lowers variance and reduces ruin risk, but sacrifices some of the long-run growth. So a quick takeaway is, as the edge grows, both the optimal fraction and the attainable growth increase. In practice, Kelly balances the long-run growth and variance, but overbetting inflates ruin risk. So, from an information theory interpretation of Kelly, if we measure growth in bits, i.e., use base 2 logs, the Kelly maximum per round becomes a simple expression tied to entropy. We'll start with the bit version. G of L equals Q times log base 2 of 1 plus L plus P times log base 2 of 1 minus L. Plugging in the Kelly optimum, L equals 2Q minus 1 gives us 1 plus L equals 2Q, and 1 minus L equals 2P. So at the optimum, G max equals Q times log 2 of 2Q plus P times log 2 of 2P. If we separate out the log base 2 terms, we obtain G max equals 1 plus Q times log base 2 of Q plus P times log base 2 of P. So now we see the binary entropy formula, if you'll recall, H of Q is q times log base 2 of q plus p times log base 2 of p, we get the following identity. So interpreted in bits, the best possible growth per round equals one full bit of potential minus the remaining uncertainty, the entropy, h of q. So intuitively, if you had perfect information about the outcome, you could convert that full bit of potential into guaranteed growth. With imperfect information, part of that potential is lost to uncertainty.